Good afternoon, and welcome to today's Vision Systems Design webcast. Our topic today, Mastering Machine Vision Inspection, Optimizing Bright Field and Dark Field Illumination Techniques, is sponsored by Advanced Illumination. I'm Jim Tatum with Endeavor's Design and Engineering Group. To begin, let me explain a little about how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box, and a member of our team will assist you. You can also click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the Ask a Question box and click on the send button. Also, please be aware that today's session is being recorded and will be available on the Vision Systems Design website within the next week. You'll be notified by email when the archive is available. Now, let's meet today's speaker. Brett Thrailkill is the application manager at Advanced Illumination, a design and manufacturer of LED lighting assemblies and controllers for machine vision systems. Overseeing the application and imaging labs, his primary responsibility is to address complex machine vision challenges, providing practical and robust solutions to clients in the field. Before joining Advanced Illumination, Brett held the position of Senior Equipment Technician at Samsung Austin Semiconductor, working in the quality management of automated semiconductor production equipment. Prior to working in the semiconductor industry, Brett served 24 years in the United States Navy, holding various roles such as Aviation Electronics Technician, Naval Air Crewman, Navy Diver, and Master Training Specialist. Brett holds a Bachelor of Science in Occupational Education, majoring in Corporate Training and Development. Now, let me turn things over to our presenter. Brett, the floor is yours.
Thank you for the introduction. Hi, I'm Brett Thrailkill, and I'm the Application Manager at Advanced Illumination. I've been running the imaging lab here for the last 2 years. Welcome to this webinar, Mastering Machine Vision Inspection. Today's topic is optimizing bright field and dark field illumination techniques. I'd like to take this time to thank all of the viewers for their participation today and look forward to taking any questions that you may have at the end. When I first started in the machine vision field, I had to drop all of my preconceptions concerning the importance of the camera versus the lensing versus the lighting. I quickly learned that the most expensive cameras and lenses could not be used to their full capacity without the proper lighting and lighting techniques. No other aspect of vision system design and implementation has consistently caused more delay, cost overruns, and general concern than lighting. Quite often, lighting was the last aspect specified, developed, and funded by organizations looking to start a new application. For this webinar, I intend to set the stage by first discussing how to properly plan an application. This would include selecting the correct illumination techniques. Then I will get into the heart of the subject, which includes bright field versus dark field. I will show you the differences between the two styles and what sets them apart. Then we will talk about full bright field techniques, partial bright field techniques, dark field techniques. I'll show you some examples of bright field versus dark field, and then we'll wrap it up with some advantages and disadvantages before we head into the question and answer period. To properly plan an application, proper lighting techniques must be addressed from the very start of a project. These techniques consist of 3 main areas of concern: the 4 cornerstones of machine vision lighting, the inspection environment, and the different types of lighting, cameras, and techniques. The 4 cornerstones of machine vision illumination include geometry, the geometrical relationship between the object which is being inspected, the light at different working distances, and the camera. Geometry is one of the most important of the 4 cornerstones, and the one discipline that you may have the ability to affect the most, especially if you plan your application around the lighting. In order to solve the geometric issues involved in a new application, you will require task-specific lighting and/or changing the placement of the camera, target, and light. For example, a standard bright field bar light may also be used in a dark field or bright field application, whereas a diffuse light is used exclusively at shorter working distances and straight on. The environment will always dictate what type of lighting can or can't be used. In this example, we see a fuel filter being imaged. The ring light looking straight down creates a lot of glare. Placing the light off axis but parallel to the object reduces the glare slightly. Placing the light off axis but perpendicular eliminates most of the glare. Switching to an off-axis spotlight with a longer working distance provides for the best image. Many issues must be considered and addressed when looking to start up a new application. Some of the physical constraints that you will face can consist of the access for the camera, lens, and lighting in 3D, the size and shape of the work area, the minimum and maximum camera, lighting, working distances, and field of view. Some of the part characteristics that you have to take into account. Is the part presented consistently in orientation and position? Is there any potential for ambient light contamination? Is the object stationary, moving, or indexed? If it's moving or indexed, what are the speeds and the cycle time? Is strobing required? If so, what would be the expected pulse rate, on time, and duty cycle? And finally, ergonomics and safety. Is there an operator in the loop for operator interaction? Are there any safety-related concerns to strobing or intense light applications, such as a bright strobe light in an operator's eyes? Application setups can vary from complex multi-camera, multi-light setups, such as this setup with 4 cameras and 5 different styles of lights, to more simple single camera setups. The second cornerstone is pattern and structure. The shape of the light which is being projected onto the object. All of the lights that I talk about today will have a varying pattern, intensity, and field of view. Wavelength is the third cornerstone. Various wavelengths are reflected or absorbed differently by each object and background involved in the inspection process. Here I have several electronic components that were tested with various wavelengths to determine the optimum color. UV, blue, green, red, white. But in this case, IR proved to be the perfect wavelength for inspecting the contacts. And the final cornerstone is filtering. Filters can be used to pass or block specific wavelengths to enhance the image contrast. This can include a bandpass filter to eliminate glare from a UV light. In this case, I was using 365 UV on a bolt with coating that was infused with UV ink. Using a bright field ring light, a lot of glare was reflected into the camera. However, once a 695 bandpass filter was applied to the light, all of the glare from the UV was eliminated, leaving a perfect image for identifying the missing coating. Polarization is another discipline that can help you solve lighting issues. Polarization in machine vision has been employed primarily to block specular glare reflections from surfaces. As simple as 2 pieces of linear polarizing film with one placed over the light and one placed over the lens. This image was captured using a flat diffuse light. The reflections off of the various angled products make it very difficult for an imaging system to recognize and categorize the products. A polarized lens was placed on the camera and a piece of polarizing film was put over the light. The polarizer on the lens was then turned until the majority of the glare was eliminated. In this case, the imaging software was then able to categorize the products by their shape and color and labels. The second area of concern is the detailed analysis of the immediate inspection environment, which consists of the physical constraints and requirements for each individual application, and the way the object interacts with the task-specific and ambient light. There will be times when a certain type of light is the best illumination solution, but because robotic pick and place is required, it just may not fit in the physical space. The shape of the objects, its composition, reflectivity, and color are all factors that have to be taken into account when choosing the correct lighting method to use. The third area of concern is the knowledge of different lighting types and their proper uses, vision cameras and spectral range, and the illumination techniques and their applications. Illumination techniques are comprised of 5 basic groups: full bright field or diffuse, partial bright field or directional, dark field, backlighting, and structured lighting, which can comprise LED grids and line lights. For today's presentation, I will be concentrating on the first 3 techniques. Most manufacturers of vision lighting products offer lights with various combinations of techniques available in the same light. These circumstances allow for greater flexibility and can also reduce potential cost when different inspections can be accomplished at a single station rather than 2. If you can solve 3 issues: the application conditions and limitations, the intricacies of the inspection environment, and the object-light interactions, you will be able to meet the following 2 acceptance criteria: maximize the contrast on those features of interest versus their background, and provide for a more measure of robustness with consistency and reliability. Bright field lighting is a method for imaging reflected light. The illumination coming from the light is reflected into the camera so that small flaws and edges which typically scatter light are not picked up by the camera. This creates a bright image, but areas with engravings, scratches, or indentations may not be as well defined. Dark field lighting, on the other hand, captures the scattered light. By imaging only the scattered light, objects, borders, and imperfections become more prominent in the image, as they tend to scatter the light the best. The seemingly complex light geometry distinctions between bright and dark field lighting can best be explained in the terms of the classic W concept. As a rule of thumb, the W concept shows that the light angles from 0 to 45 degrees is referred to as dark field, and angles from 45 to 90 degrees is considered bright field. You can imagine from this image that the closer you move the bright field light to the camera, the smaller the reflection angle becomes and the more glare that you will create. The DF light demonstrates the opposite, and the lower you move the light, the less light that will reflect back into the camera lens. Here's an example of the differing geometry setup of a bright field ring light versus a dark field ring light. Notice the difference in construction and geometry of the 2 lights. Not only is the bright field ring light further from the target, creating a more solid light angle, but the LEDs are pointed straight down. Whereas the DF ring light is close to the surface and the light pattern is much more aimed. That's due to the LEDs in the dark field ring light being physically aimed at a target during the production of the light. When using bright field lighting, specular surfaces reflect glare if light is high angle. Here you can see how flat surfaces bounce the light back into the camera and imperfections deflect the light away. The diffuse, flat, and smooth surfaces reflect evenly. This gives you the bright field with the dark defect appearance. Dark field emphasizes height, edges, shape, and contours. In contrast to bright field, you can see that the flat surface bounces the light away from the source and the camera, while the imperfections deflect the light up towards the camera. The flat polished surface becomes dark. This gives you the dark field with the bright defect appearance. Bright field can be divided into two sub-techniques, differentiated primarily by solid angle, which is generically defined as a measure of the amount of relative area from which the light is sourced. Those two sub-techniques are bar lights, spotlights, and ring lights, or any light at significant working distance with a relatively small solid angle. These lights are termed partial or directional bright field point sources. Conversely, large solid angle, hemispherical or planar lights, such as diffuse domes or coaxial diffuse and flat arrays, are all termed full bright field sources. It's important to consider that in general, full bright field lights are most effective when placed relatively close to the intended inspection surface, as they provide a larger solid angle. This creates a more diffuse light projection known as cloudy day illumination, which assists in inspecting reflective or widely different surface textures and elevations. For that reason, it's important to note that as the light's working distance increases, its solid angle decreases. This renders the full bright field light's diffuse and multiple angle light geometry effective, more typical of a partial bright field light. Why is this distinction important? Because each combination of light presentation, geometry, working distance, and solid angle has its own advantages which depend on the inspection part's characteristics, features of interest, and part access considerations. Full bright field or diffuse lighting is commonly used on shiny, specular, or mixed reflectivity parts where even light but multi-directional, multi-angle light is needed. Domes, flat arrays, and on-axis coaxial lighting are the primary types of bright field lights. Diffuse dome lights are very effective at lighting curved, specular surfaces commonly found in an industrial workplace. Dome lights are most effective because they project light from the multiple directions, 360 degrees looking down the optical axis, as well as multiple angles from low to high, which tends to normalize differential surface reflections on complex shaped parts. They provide light that is similar to the light on an overcast day. They minimize light source glare. They are useful for curved, specular, reflective parts, and the surface texture and detail are de-emphasized. Image A shows the bottom of a soda can illuminated with a bright field ring light, but shows poor contrast, uneven lighting, and specular reflections. Image B is imaged with a diffuse light, creating an even background, allowing the code to be read. On-axis lights work in similar fashion as a diffuse dome or flat objects, and are particularly effective at enhancing differentially angled, textured, or topographic features on otherwise planar objects. The light is directed at a beam splitter, the surface texture is emphasized, and angled elevation changes are darkened. These next set of images were taken with a small dome light. On these two images, you can see the viewport where some of the reflected light is lost through the hole and leaves a shadow on the target. Several different things were tried to reduce this effect, including moving the parts off-center, but nothing seemed to work satisfactorily. After some further testing, an unconventional method was used to provide a suitable solution. A coaxial light was stacked on top of the dome light, and the result was that the shadow from the viewport has been softened and almost entirely eliminated. The result was a much better picture for inspection purposes. This solution just helps to reinforce the idea that the proper application of the four cornerstones of machine vision lighting techniques are crucial for solving your application dilemmas. Flat diffuse lighting may be considered a hybrid of dome and coaxial diffuse lighting. From a lighting geometry standpoint, it produces more off-axis light rays than a coaxial light, but fewer than a dome light. You may hear the flat array referred to as a flat dome light. Because the flat diffuse light is direct lighting, rather than internally reflected from within a dome light to the object, this light can be deployed over a much wider range of light working distances, especially longer than working distances not possible with a dome light, as long as the flat dome is oversized. A flat diffuse light directs a diffuse sheet of light downwards towards the target. It allows for longer working distances and a larger field of view. Here we have a tray with 384 wells. Each well bottom has a laser-etched 2D code. The first image is using high-angle ring light with limited results. The second shot is a DF ring light with good results, but you can see some shadows that might obscure some codes. The third image is a coaxial light, which might work well enough, but could still raise issues. The fourth picture is a diffuse dome, which completely washes out the code. In the final image, a flat diffuse light is used and provides a nice clear image of the codes. Here's a side-by-side comparison to see all of the differences. I used a large cylinder light at 25 millimeters for the image on the left. While it gives a nice flat picture like on a cloudy day and eliminates the glare, the flat diffuse light at 220 millimeters on the right did a superior job of highlighting the discrepancies on this aluminum packaging material. This image showcases one of the major advantages of this light and gives you another lighting option when planning your application. As you can imagine, anytime you are imaging multi-contoured plastic packaging, reflections can be a terrible issue without the correct lighting technique. In this case, while trying to reduce the glare, the package was being inspected to ensure that the proper amounts of glue had been applied to hold the plastic cover down to the cardboard. A flat diffuse dome light was used to highlight the glue around the edges of the package to locate the proper and the improper seals. Partial bright field lighting is the most commonly used vision lighting technique and is the most familiar lighting we use every day, including sunlight, lamps, flashlights, etc. It's typically produced by spotlights, ring lights, or bar lights. Because of its directional nature, it's a good choice for generating contrast and enhancing topographic detail. This type of lighting is distinguished from full bright field in that it's directional, typically from a point source. It's much less effective, however, when used on axis with specular surfaces generating the familiar hotspot reflection. This is a small, high dispersion bright field ring light. The non-lensed LEDs disperse light at broad angles, providing soft lighting for the applications that require short working distances. Diagram A just once more re-emphasizes the difference between partial bright field and dark field. The picture labeled B is an example of high angle light from a ring light reflecting on a specular surface. The glare from this angle makes reading the 1D barcode impossible. However, if we move the light off axis, we can improve the image for the camera in order to read the barcode. This image was taken using a bar light from a bright field angle from the left across the tool. Notice the uneven distribution of the light across the part and the shadowing on the left side. This image was taken with a bright field angle from the right and the shadowing on the right. This shot was taken with both lights illuminating simultaneously, which eliminated the shadowing and allowed for perfect label placement. Dark field lighting is perhaps the least well understood of all the techniques, although we do use these techniques in everyday life. For example, the use of automobile headlights relies on light incident at low angles on the road surface, reflecting from small surface imperfections in other objects. Dark field lighting can be subdivided into bar lights, aimed ring lights, and spotlights. This type of lighting is characterized by low or medium angle of light incidence, typically requiring a very short light working distance, particularly for the ring lights. This dark field light has precisely aimed LEDs which provide a specific and repeatable light pattern on the imaging plane. This dark field ring light provides a very low angle of incidence and creates a radioillumination pattern. I will show you some examples using these lights demonstrating the low angle light that they disperse. Effective application of dark field lighting relies on the fact that much of the low angle light incident on a mirrored surface, less than 45 degrees, that would otherwise flood the scene as hot spot of glare, is reflected away from rather than towards the camera. We call this angle of reflection equals angle of incidence. The relatively small amount of light scattered back into the camera happens to catch an edge of a small feature on the surface, satisfying the angle of reflection equals the angle of incidence equation. Sheetrock can present a particularly difficult surface for machine vision inspection. Even under bright room light, the imperfection in the surface is hard to detect. But using a bar light at a very low angle allows this ridge to be detected and for this sheet to be rejected. And here's a side-by-side comparison to highlight some of the challenges that we can face. Here's another example of a very difficult imperfection to detect. It should be noted that if the bar light is moved to a bright field angle, the defect disappears when the shadowing fades. Likewise, if the light is moved to a perpendicular position from where it is shown, the defect also disappears for the same reason. This creates a challenge which can only be overcome with multiple lights at multiple angles when this inspection is being performed on similar material traveling down a conveyor belt. For this application, I was tasked with locating an ID tag on a rubber tire sample. As you can see, using only ambient light, there is no contrast between the rubber and the tag, and it's almost impossible to see. A bar light was positioned down low and close to the rubber material, which provided the necessary shadowing needed to locate the black ID tag on the black background. Utilizing software, the lookup table helps to enhance the contrast for the inspection process. This is a solid silver coin, which has corroded over time. You can see that the lettering at the top is not legible. Low angle light helps to penetrate the corrosion to inspect the coin. The dark field light highlighted the edges as well as the middle of the coin. Here I will show you some direct examples comparing bright field lighting to dark field lighting to emphasize the contrast produced by the different angled lighting techniques. The next images are 3D printed samples, which were imaged to analyze and obtain the true dimensions of the internal structure. The goal of this exercise was to highlight some of the internal features of this 3D printed object. The same dark field ring light was first used at a bright field angle of 100 millimeters, then lowered to 15 millimeters to demonstrate the contrast. You can see that the bright field angle only highlights the top of the structure, while the dark field angle gives good depth to the layer below. This last structure had edges that were slightly curved upwards. While you can't see it using the bright field angle, the shadowing created using the dark field angle makes it very apparent. Notice the contrast between the bright field diffuse light at 75 millimeters working distance and the low angle dark field light at 12.5 millimeters working distance. Both coins are highlighted nicely, but the bright field diffuse light provides a much sharper image. Note, too, the contrast in the stars and the stripes on the American flag. I imaged a poker chip for this next example using a small dome light and an aimed dark field ring light, both lights at 10 millimeters working distance. The dome light gives a clean but flat image, while the aimed ring light adds a lot of depth to the image and highlights some of the defects on the chip. As is the case on a cloudy day, contrasts based on topography differences are de-emphasized when using a dome light, as opposed to low-angle lighting from the aimed ring light. You get a much greater sense of depth from the image on the right. However, you also lose the edge of the chip with the ring light and get a better outline with the dome light. For this next set of images, I used a very popular bright field dark field ring light. This light is more diffused and less directional than a typical dark field light. It provides diffuse illumination at a low angle to cast shadows used to identify surface defects, emboss text, etc. It can be used as a bright field ring light when the outer diameter is smaller than the working distance. When this concave disc is imaged with ambient light, you can just make out a character in the center and the numbers at the top of the disc. Using the bright field dark field ring light at 155 millimeters, the middle of the disc is illuminated and the characters in the center of the disc are now legible. The numbers at the top are almost invisible. As the light transitions from 155 millimeters down to 50 millimeters, the center disappears and the dot matrix numbers begin to appear. At 20 millimeters, the dark field image is in full effect. Finally, this video shows the transition in real time from bright field to dark field on the concave disc. You can see here at the start that we have a bright field image, though the center is darkened due to the curve of the target. As we get closer to the disc, the background becomes very dark, but the numbers at the top begin to appear until the characters finally come fully into view for imaging. Dark field effect with a bright field angle. The final shot of this disc gives an example of a high-angle dark field image. This goes against the industry standard norms of what dark field lighting is. A small bar light is positioned close to the camera at a bright field angle, but due to the concave structure of this disc, a dark field image was captured. A lighting application should never limit itself to a conventional thinking if an outside-of-the-box setup is the only solution. Using a bar light at 160 millimeters working distance, the code on the disc was imaged in the same way as it was using the ring light at 20 millimeters. Showing a side-by-side comparison, you can see that both techniques accomplish the inspection goal. Having two solutions allow for more flexibility when it comes to designing a machine vision system. My final slide in this presentation is just a quick overview of some of the advantages and disadvantages of the lights I talked about today. As you work with these lights and become more familiar with their use, you will find many more advantages and disadvantages of one method over the other. Each application and selection of the proper light is wholly dependent upon what you are inspecting it for, and the four cornerstones of machine vision. Here are some of the advantages and disadvantages of the different categories of the lights I discussed. Partial bright field light is preferred when target is non-specular or for area lighting. One great advantage is that it may be used as a dark field light. Also, there's no working distance limit, though it is intensity dependent, and partial bright field lights may be positioned at multiple angles. A disadvantage of bar lights and spotlights is that they may cause uneven uniformity across the target and, of course, reflectivity on specular surfaces. Dark field can be used on specular and non-specular targets, used for surface inspection, edge detection, and transparent parts. Dark field lights are good for emphasizing height, edges, and contours, for finding defects in mirrored reflective surfaces, and reading barcodes beneath reflective covers. However, the light must be very close to the part. It can have a large footprint, a limited spot size, and ambient light may be an issue. Coaxial lighting is preferred for relatively flat, specular surfaces that may also exhibit reflectivity differences based on elevation, contour, angle, or composition. With coaxial lighting, ambient light is usually not a factor, and it is good for enhancing angled or textured features. As with dark field lighting, the light is close to the part. It is also a large footprint. The beam splitter reduces the illuminance by 50%, and you may lose your depth contrast. Dome lights are beneficial on specular and curved surfaces where uniform illumination is required. If ambient light is an issue, one solution can be using a dome light to keep it out. Dome and flat dome lights are good on curved, complex shapes, and the flat dome has a greater working distance and a larger field of view, as long as you oversize the light. The dome light must be very close to the part. It will have a very large footprint. The camera will be close to the light, and you'll have a smaller spot size, usually 1/2 the light's inner diameter. If you'd like to follow up with me at a later point in time about this or any other subject, or any other questions that you may have concerning machine vision lighting, please feel free to call me at 802-767-3830, extension 227, or drop me an email at bthrailkill@advancedillumination.com. I'd be happy to follow up with you. If I can't answer your question directly, I can certainly find the right person here at AI that can. I would also encourage you to download our practical guide to machine vision lighting. This comprehensive handbook covers everything I talked about today and much more. If you're looking to get into the machine vision lighting industry or would like to refresh principles that you learned in the past, this industry-leading lighting guide is the best place to start. You can also download a copy from the VSD resource page. I'd also like to take a moment to introduce Daryl Martin, our Technical Sales and Product Specialist. Daryl is the author of the Practical Guide to Machine Vision Lighting. He is also an instructor of the A3 Vision and Imaging Certified Vision Professional Certification course. If you have taken the CVP course at a trade show, such as Automate, you may have already met him. Daryl will be joining me during the question and answer period. Again, I would like to thank you for your time, and with that, we'll jump right into any questions that you may have.
We are going to jump right in. If you'd like to submit a question, remember, just type your question into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. And without further ado, let's see what we've got. Quite a few good questions here. We have one. Can you explain why there will be a circle formed in the dome light image and how to avoid that?
All right. Well, Ashwar, that's a good question. I did cover that in the presentation with that picture of the coaxial light put over the dome. It was something that I kind of tried as a last resort, and it turned out really well. The light that bounces up into the dome and comes back down, if it's on a very specular surface, that light bounces back up and it escapes through the hole in the dome, and it gives you that little shadow look. And then if it's a flatter, less specular surface, you won't notice it as much.
Okay. I guess following up to that, in the coaxial light image, the light won't be proper at one end, with the light being brighter at one end and the other will be less bright. How do you avoid that?
Yeah, that's a really good one. That's that was by Ashwar as well, and that has a lot to do with the distance that the light has to travel. And I think I'm going to defer this one over to Daryl. He's usually got a really good explanation for this.
Okay, thanks. Thanks, Brett. No, that's a good question, a very legitimate question as well, Ashwar. Essentially, what it comes down to is, as Brett said, that the light travel distance is a little different from the top of the light down toward the base. Now, obviously, the light that's hitting the beam splitter at the top is traveling a lesser amount when it hits the splitter, but and then say what's at the bottom. However, I think what's important to know is that the beam splitter itself is a 50-50 splitter. So in other words, half of that light is being reflected down toward the surface. The other half isn't. So basically, you're pulling 50% of the light out in a different place in the light's path, and so ultimately that's probably the main reason for the drop-off. It's not an easy one to try to explain, but you see it pretty commonly in most of these types of lights. When we started building these lights, they were much smaller versions, and so they tended to not really show that as much. When you get to these very large models that are offered nowadays because of the application requirements, it is more noticeable. The really only best way to combat that, I think, and we've tried to do that with diffusion, but there's a limit there as well, is probably to have, an alternate row of lights, LEDs or whatever the case may be in the source, that are more intense in one area versus the other. But that's really a very custom job, and obviously there's a couple of post-processing applications you could work with too, to flatten the field a little bit. More or less successful probably, but again, that's a post-processing operation, and sometimes if it's a high-speed application, you don't have a lot of turnaround time between parts, for example, to do that kind of thing. But anyway, that would be my answer.
Okay, another question coming in. In our previous attempt to use cross-polarization, we had issues with warping the polarizer in front of the light. Do you have any suggestions for working around this?
Yeah, go ahead, Brett. Sorry.
Well, I was just going to say, I assume that he's putting a piece of film across, and if the light's pointed down, you're going to get some warping. Now, I'll only do that for testing purposes if I don't have a light that's already polarized. The very best way around it is the lights that we build. You can purchase with a lot of them with the polarizer option, where we actually stick the polarizer under the lens, so it's part of the light. And that's really going to be the best way for you to avoid having the warping of the polarizer in front of the light.
Okay, and then follow up to that, it looks like on the cross-polarization example, was the exposure time increased significantly to produce a similar image without glare?
So for this one, quite often you want to turn off your exposure time. I actually, for these images, for a specific reason, had it turned on. So I can't tell you exactly how much it increased. Daryl, you got
Yes.
anything you can add to that?
Right. So ultimately, right. Polarizing film will, by definition, drop your intensity 50% when that light passes through it. So, you've got a light loss. Also, what's important to note is that the part of the issue with the polarizer not holding up is just because it is absorbing a tremendous amount of photon power. So the stronger the light is itself, the more heat that's generated inside the light head will cause the polarization film to buckle. We have instances where high power LED lights can literally burn the film in a matter of hours of on time. And that's in part because of the photon power, but is also the photon wavelength. It looks like the shorter wavelengths tend to quickly burn the polarizers more so than the longer wavelengths. So yeah, the one of the ways around that is to go with an alternate type polarizing material, wire grid or something along those lines. The issue there is, of course, that they're a little bit harder to work with if you have multiple lights, multiple sizes, etc., and they're quite expensive. So those are the primary, other than what Brett had mentioned, primary ways to get around this. There's also glass sandwich film available from various vendors. That seems to be a little better, but once again, you're still pushing a lot of power through that polarizer, and if it's only passing 50% of the light, it has to absorb that other 50%, and that creates heat.
Okay. Is there a wavelength that is best for dark field imaging?
So that's a really good question. Blue is quite often a better wavelength because the shorter wavelengths tend to scatter the light more. As you go up in wavelength, you'll get a lot less of that scattering power, and that's a tough question because I use a lot, depending on the camera. I use a lot of white, but then again, white has a lot of blue in it. So the blue wavelength really is one of your best wavelengths to start out with.
Yeah, I can offer an example there, Brett, if you don't mind. Yes, essentially, it depends a little bit on the exact surface and parts that you're viewing. For example, we did a test a few years ago with laser etching, and the customer, because of the particular application, was using red light, and they were not getting much in the way of a reflection back, so they couldn't read the laser etched human readable code on this metal part. And it was a matte metal part, by the way. So we switched to a blue light, and it immediately popped the laser etch. So again, this is probably Brett mentioned this in the presentation, but oftentimes it's a matter of testing to see what works best.
Right, and I would also throw in that presentation, the picture I showed of the electronic components. I was using a small dome light on that, so it was dark field. And you notice that the IR was actually what worked the best. So it also comes down to what you're imaging, the part that you're imaging is really crucial. So as Daryl said, I went and tested with each wavelength until I found the one that worked the best.
Okay. What percentage of vision applications is dark field, by the way?
Well, if you go by the lights that we build and we sell, probably 10 to 20% are dark field, bright field, because there's so many different applications, so many more things you can do with them. Probably tends to be about 60%, and then backlighting probably makes up the 20. Backlighting and line lights probably make up 20 to 30%.
Okay.
Yeah, it's also highly dependent on the application too, or the market that a particular customer is working in, or what you sell into, frankly. So if you're in the semiconductor field, dark field is much more important. Whereas we tend to be more general ourselves anyway, tend to be more general industrial manufacturing inspections.
Yeah. Is there a limit in the diameter a dark field light can be?
No. But of course, as the distance of the light has to travel, the intensity is going to fall off. So as that happens, your uniformity is going to suffer. So we've made some very large domes in the past, but you do run into some, depending on the work distances, you can run into some issues with just what you can use on a system.
Yeah, no, the other issue, of course, is cost. So obviously a large dark field ring light, for example, is going to be, rather expensive.
Yeah.
Okay. Can dark field lights be built to be IP65 or IP66 compliant?
They can. We have several. We even have some that you could use for IP69K, high power washdown. We have bar lights and spotlights that can be IP69K. We have bar lights, spotlights, and a number of ring lights that can be IP65 and IP67.
Yeah. Just one quick one. Why do dark field lights need to be placed close to the part?
Well, as you saw in the presentation, it's all comes down to the amount of light at low angle that hits the surface and scatters, and then if you hit that scratch in a piece of glass, the lower light, you're going to have more bouncing back into the camera. I think the best example was using the sheetrock. I had to go extremely low. This was a piece of sheetrock I held in front of me under a light, and I could hardly see what was there. And it took a bar light at a very low angle to even show the shadow. As soon as I brought that bar light up to a certain, a little bit higher, I completely lost the shadowing and I lost the defect.
Okay. What's a good way to avoid being in the family of angles with large field of views larger than 10 feet ROI?
Can you repeat that one again?
Yeah. What is a way to avoid being in the family of angles with large FOVs larger than 10 feet ROI?
What is the way to avoid? Daryl?
Right, yes. I was looking at this one. Not quite sure exactly what is being referenced here, but if I'm understanding the question properly, a large field of view, meaning larger than, say, 10 feet, yeah, that's a large, extremely large area. And if you're looking at working with dark field, you're almost at that point looking at, multiple bar lights at very low angles, I think, obviously, as Brett just alluded to with respect to the sheetrock example, if that answers the question.
Okay, I think there was one more. Dark field, does dark field require a ring light or can other lights be used? I think you've gone through that, but just to reiterate.
Yeah, just to reiterate, the dark field ring lights can be very effective, but you can't use a ring light in every situation. Dark field comes down to the low angle light. So you can get spotlights and you can put them at low angle. You can get bar lights, put them at low angle. The nice thing about the ring lights is you'll get a different perspective, but sometimes you might just have to take 4 bar lights and put them in a square pattern to give you a ring light effect, but it all comes down to having the light down at a low angle to have your dark field.
Yeah, what I can add to that, Brett, is your good example was the coin you showed earlier. You had multiple directions, basically reflection directions, and you're never going to pick all of those points up unless you have a circular dark field. So in that case, it was pretty critical. As you pointed out, you could also use, if it was a large area, you could also use multiple bar lights in a sort of a picture frame approach. But yeah, sometimes if you have a setup like that coin, you really do need circular dark field as opposed to linear dark field.
Good answer.
Okay. If there are no other questions, we did have someone who said they were having a little bit of technical difficulty seeing the presentation. I just want to reiterate that this is being recorded and will be available to everyone. We'll be on the Vision Systems Design website. We'll be emailing everybody when that happens. So if you were having trouble or you got here late, you'll be able to see it again on our website. If there are no other questions, did y'all have any other thoughts or reflections to add to this?
I would just encourage anybody who's got any follow-up questions or come up with any questions, just please reach out to me and we'll get you the answers to your questions. Please download that practical lighting guide. You will find it incredibly useful, and I promise you'll be happy that you download that guide. Daryl, any last thoughts?
No, I think you covered it well, Brett. Thank you, though, everybody.
All right.
Okay, well, thank you both for that great presentation, and that concludes today's presentation. On behalf of Vision Systems Design, I'd like to thank Brett for an excellent presentation, as well as Daryl, and thank Advanced Illumination for sponsoring today's event, and of course, thank all of you for joining us today, and we hope you have a terrific rest of your day. Thank you.